We're going to talk about the motor unit, its anatomy and physiology in this video. It is the basis for EMG understanding, and here we start with the normal motor unit, which consists of a motor neuron, the axon, the motor end plate, and the muscle fibers, often 25 to 200 muscle fibers depending on muscle. The motor unit muscle fibers, they are intermingled with other motor units, so in a cross section we can see representation from different motor units. There are a few reactions to pathology. One is myopathy, where the motor neurons are more or less normal in number. We have in the periphery muscle fiber atrophy and hypertrophy, longitudinal or cross-sectional splitting, loss of muscle fibers, and increased interstitial tissue. The territory is more or less unchanged or little small. In re-innervation, we have the following situation. After denervation of one axon here, its muscle fibers start to show spontaneous activity, and within a very short time, a few days, nerve sprouts are growing from the surviving motor units and innervate the denervated muscle fibers. So the surviving motor unit now will contain more fibers than previously. Here is a new technique to look at motor units. It is an ultra-fast ultrasound technique where we see the first motor units recruited after a minimal effort. And little stronger activation, we see more motor units coming in, overlapping with each other. And here's a schematic, a drawing of the same thing, with the territory of the motor units overlapping with each other. They are in principle roundish, except in the periphery where they may be elongated. The diameter is 5 to 15 millimeters, and the fibers within the territory of a given motor unit are randomly distributed. If we look at the small area here corresponding to the view area of a microscope, we can see representation from many different motor units in this small area. Each motor unit is here represented within a square millimeter of about 250 fibers, and we see many different motor units in this area. Each motor unit contains, as I said, 25 to 200, 300 muscle fibers, and it's about 300 micron distance on average between muscle fibers in a motor unit. The motor unit can be classified in many different ways. One is the histochemistry and the metabolism, which is the same for all fibers in a given motor unit. And a simple classification is type 1 and type 2 with under or subclasses. The type 1 are slow aerobic, fatigue resistant motor units, and the type 2 are fast anaerobic, glycolytic, and fatiguing muscle fibers. The fiber size is about 50 micron on average, and we usually have only one motor end plate per muscle fiber. The end plates in a cross-sectional area is represented like a end plate band of 5 millimeters, and I will come back to that later. Here is the mechanical response to a nerve impulse. Usually in the EMG lab we do not measure this, but perhaps we should do that in future. Here is the electrical event. It can be one muscle fiber, or in this case I have been thinking of the C map. And after a short while this is followed by the mechanical twitch that reaches the maximum here after some 100 milliseconds and then returns to normal, and is dependent on cooling, fatiguing, and so on. Electrophysiological parameters of the motor unit is as follows. The anterior horn cell, we have the monosynaptic connection between the corticospinal tract and the afferents, and we also have polysynaptic connections with interneurons that regulated the firing rate. The firing pattern can theoretically be divided into tonic and phasic types, but when we look at a large group of muscle fibers with different types, it is difficult or impossible to see a clear differentiation in two distinct groups. It seems to be a continuum. Size principle means that successively larger motor units are recruited upon increasing force level. We talk about jitter in the motor end plate, which is of the order of 15-20 microseconds, but we have also a time uncertainty in the motor neuron, the H reflex jitter, which is up to 400 microseconds. I will talk a little about the phenomenon of re-innervation after denervation. Here we have the territories of two motor end plates, one here and one here, indicated with black and white muscle fibers. If we have an axonal damage to one of these axons, we have denervation in these white muscle fibers, and after a short time we start to have collateral sprouting. That means the growth of new nerves from the survivor, the black motor unit here, over to the earlier denervated muscle fibers. And we now will get clusters of re-innervation within the motor unit. But this black motor unit does not help the fibers outside the black original territory. So these fibers have to be rescued by other motor units that are overlapping here, not seen in this sketch. This is called collateral re-innervation. The other type of re-innervation is when we have a complete nerve cut. Then the only way for re-innervation is the new outgrowth of terminal axons here that contact the muscle, take one fiber after the other in possession, and we have very dense groups of muscle fibers here. The very first thing that happens here is then that the motor unit consists of only one muscle fiber, and then a few, and then more and more. The first motor units of small amplitude and duration are called nascent motor units. But in the more commonly seen type of re-innervation, in the partial lesion, in the EMG labs, we usually see this type, the collateral re-innervation, and there we never have the nascent motor units. We always have the mother motor unit, here indicated in black, that in addition will recruit muscle fibers and re-innervate them. Here we see a rat muscle where it has been experimental denervation of very slight order, and you see that after some time many fibers cluster together with the same histochemical type. This is measured by looking at one fiber, and if that fiber is surrounded by similar histochemical type of muscle fibers, then we talk about the grouping. Here we see small groups, and this is another chronic and more pronounced denervation, and this is the result after re-innervation. Really very early, when we started to know about collateral re-innervation in 1950s, Coers and Wolf in their book described this phenomenon of re-innervation. Here we have the normal situation, and 4 of these axons have been lost due to damage, and we have only one muscle fiber surviving. And from that axon we have an outgrowth of small terminal nerve twigs that take physiologic contact after a week or a few weeks, and then more and more mature, and we end up with a situation that is similar to the previous one, maybe a little changed in morphology, which we have learned over the years. We made a simulation about the way we can visually assess the degree of motor axon loss, namely by taking away 10% of the motor units and let the survivors re-innervate the denervated fibers. And we try to see here, after 10% loss of axon, do we see any grouping at all? We are not sure about that after 10 or 20%, but when we have 30%, we can see that some fibers of one type are surrounded by the same type. So here we really have small groups, and this is more and more clear the more of axonal loss we have. Here is a situation in motor neuron disease where we have fiber type grouping. We have this fiber surrounded by the same type of muscle fibers. We have this fiber surrounded by the same type. When these groups now become denervated, when the nerve fiber to these groups is lost, and we have a degeneration of that motor unit, then we also have a degeneration of connected muscle fibers, and we have smallness and atrophic muscle fibers. So this is grouped atrophy. Here is before we have grouped atrophy. Here is large grouping with one type of fibers surrounded by the same type, and here is the other type of fibers surrounded by the same type. In this picture we do not see the grouped atrophy, we only see the type grouping. I had shown this picture before, and this will be the basis for my other discussion of the motor unit. Here we have tried to look at the geometrical distribution of muscle fibers within a motor unit. We have a triggering electrode here that record one muscle fiber action potential from one motor unit and trigger the system. And then we have a motor pulling another electrode through the muscle. And time-locked activity recorded here relative to this action potential must come from one motor unit. So this is a way to get a cross-section of the motor unit. Unfortunately, not necessarily in the center of the motor unit, but somewhere in its periphery. And here we see how the muscle fiber action potentials are seen when we have 50 micron between each step. The whole thing here is 20 millimeters, and here is about the distribution of 10 millimeters. And you see the great variation and some later components here also belonging to the same motor unit. These are other things that we can discuss. We can also transform these pictures into color and get an impression of the profile of muscle fibers. Here's the longitudinal part of the muscle and the so-called end plate zone, which is said to be about 5 millimeters in biceps, for example. But when we look at just one motor unit, it looks like this. Here's the axon and its terminal nerve branches. And when it comes out closer to the muscle fibers, the motor end plates belonging to one motor unit seems to be much more concentrated with very small bands. And this can be called fractions within the motor unit. And here is again a scanning picture where we have the whole thing 20 millimeters, and you see the different shapes that we see in the scanning. In normal EMG we insert the needle here somewhere and record only one of these sites. Here is the situation in a motor neuron disease, and you see that the relative distribution here is about the same, and it's more complex here. We have some late components here, and the whole area is filled up with signals. This is the normal and re-innervated part. Here we have normal and myopathy. Again, a normal motor unit that has different fractions corresponding to the different small nerves I showed before, and you see here. And nearly the whole motor unit is filled up with signals. In contrast, in myopathy, we have first of all polyphasic areas here and here, and we have areas that are empty of signals. So that means that we have muscle fiber loss here and here. So we have silent areas within the motor unit. And a statistical analysis shows here the total diameter of the different motor unit: normal, neurogenic, myogenic, and you see neurogenic is only increased very little. Polyphasicity is increased in myopathy, and the silent areas is increased very much in myopathy, and it's less of silent areas, even less than normal, in neurogenic condition. And then a little about the physiology of the motor units. Here we have the spinal cord and the corticospinal tract. We have some activity going on, and when the firing threshold is reached for one motor neuron, it starts to to create and generate action potentials along the axon. It starts with a frequency of 5 to 7 hertz depending on muscle. If we now increase the activity a little more from central structures, then we reach the threshold for the next motor unit that in turn starts with low frequency, and the first one is now activated with a higher frequency. And this goes on like this. Now we have a very high pressure on the black one here and just newly recruited red motor unit here. This was a very schematic, and here is experimental from Carlo De Luca and his collaborators, where we have the time here and different motor units here. And this motor unit starts with a low frequency, and with increasing force the firing rate goes up more and more. And after a little while, next motor unit comes in, the next, and they all start with the low frequency and then increase in frequency up to the maximum. And then if we relax the muscle again, then they disappear in reversed order. Here is another recording that is made by Sanjeev Nandedkar, where we have the firing of one motor unit here. It starts with 8 hertz and increases with increasing force, and goes up to about 14 in this case, and then with relaxation it goes down again. And here comes in another motor unit that starts in this case with 6 hertz and goes up to 16 hertz. And here is another motor unit that goes up like this. And an interesting phenomenon here is that when number 2 comes in, there is a relaxation of number 1. The firing rate goes down a little as an unloading of the muscle spindles. And if we have the third motor unit coming in, then the already active motor units will show a slightly lower firing rate at that moment. This is not anything that we that we use clinically, but the general tendency to look at recruitment order and recruitment frequencies is used in some countries as a quantitative measure. That method, however, is little difficult. It's difficult to define which signal should be used, and there are also other problems. Here I want to show that. Here we have a slight voluntary activity with 2 motor units active. We insert the needle until we can have sharp signals. That is called that we are in focus. And we have activity the green motor unit with the same shape all the time here, and the yellow motor unit little more in the outskirts. It's one representation here. If we now increase the force a little, then a new motor unit is coming in, this blue one with a new shape, but also a new motor unit is active far away from the electrode and therefore not recorded. And then if we increase the force even more, one motor unit may be situated here, in this case on the shaft of the cannula that is used as reference, and we see a small low amplitude signal that in principle is upside down because we record between the tip and the cannula, and now if activity is only on the cannula, it will be upside down like this. So you see, when we recruit new motor units, they are not necessarily in the tip of the recording electrode, so it can be a little difficult to understand the recruitment pattern. I want to give a few examples of the physiology of the individual muscle fiber. One thing was that we could measure the propagation velocity along muscle fibers with a multi-electrode with 2 rows of small electrodes, and the fiber was positioned in such a way that the muscle fiber is passing across the electrode, and now we get two identical signals, one first from electrode 1 and the other is from electrode 8, seen here. And from the distance in the microphotograph and from time measurements here, we can calculate the propagation velocity. And I will just mention two aspects. One is that during voluntary contraction, here is 300 seconds, the propagation velocity, which starts at 4.5 meter here, goes down continuously down to 4 meter per second. And this is go from 3.6 down to something like 2.6. So that is a typical thing. It happens to most of the fibers, but not all. And we can hear that with the surface EMG that signals become more dull. And we can also hear that with the needle recording during continuous activity. Another phenomenon that we saw is the following. We have a traveling impulse coming from the right and going to the left here. Directly after the passage, we have the well-known refractory period. And a little later, we do not just get into a normal situation, but we have supranormal excitability up to 1 second after this passage. And then it goes down to normal excitability and velocity again. Here is the same thing with the double pulse stimulation. You get this velocity at first pulse and nothing happens during 3 milliseconds, and then we have a faster velocity for a few hundred milliseconds, and after 1 second it is normal again. It's very long recovery phase here, which is dependent on ion changes along and inside the muscle fiber. This is very predictable and follows strict mathematical rules. So if we know the interval between impulses and when we know the starting velocity, we can calculate the successive velocities and see how it varies when we have a variable propagation velocity. This is disturbing when we record the jitter, and also it is reflecting phenomena, as I said, inside the muscle fibers and changes in some typical ways with pathology. I don't go into that because we do not measure this regularly. The electrophysiological methods that we can use to study the motor unit are different depending on where we want to look. For the anterior horn cell, we can look at reflexes and firing pattern. For the nerve, we can actually look at conduction velocity not only in the entire nerve but in individual axons with our routine equipment that we have. There is also a special technique called microneurography, where we go close with an electrode inside the nerve to record different phenomena. And motor unit number estimation, which are a group of techniques that we can use to follow loss of motor units. The neuromuscular junction, there we look at single fiber EMG jitter and repetitive stimulation. and the muscle unit, that means the motor unit with its muscle fibers. There we look at EMG, and in some labs also the twitch. And the muscle fiber itself and its activity can be studied with single fiber EMG. The different techniques have different advantages and pitfalls and so on. Here I want to compare three parameters. In the normal muscle, we have motor units of different size. We have normal small and normal large motor units. In re-innervation, we have the larger motor units, and in myopathies, we have the motor unit with a sparse number of muscle fibers. The motor unit amplitude, motor unit potential amplitude that we measure as routine, that does not differentiate on the size of motor units, because the recurring area is say 0.5 or 1 millimeter only, compared to the total size of a motor unit that is 5 to 15 millimeters. So we only see a small part, and we do not differentiate that. In re-innervation, we have large motor unit potentials, and in myopathy, we have smaller motor unit potentials. The fiber density also does not detect any difference in small and large motor units. In re-innervation, we have increased fiber density, concentration of muscle fibers, and surprisingly enough, we also have that in myopathies, and we think we know why. And in the macro EMG, which is a recording where we can get the whole electrical activity from the motor unit, we see small signals in small motor units and large signals from large motor units. We have large signals in re-innervation and normal or small motor units in myopathy. Okay, so you see that individual techniques or parameters do not necessarily differentiate the different phenomena, but by combining two of them, we get quite a good information. For example, if we have a large macro EMG, that means a large signal, electrical signal of the total motor unit, and normal fiber density, then we are recording from a normal large motor unit. If we have increased fiber density, that is definitely an abnormality within the motor unit, and if that is seen together with increased motor unit potential size, then it's re-innervation. But if the increased fiber density is seen with a small motor unit potential, then we are talking about myopathy. And here is another such comparison with our different methods for neuromuscular junction problem, myopathy, denervation, re-innervation, axonal loss, conduction block, and central lesion. The single fiber EMG concentrates on neuromuscular junction, and we see differences in myopathy and in neurogenic condition. Conventional EMG is even better, because here we see abnormality in the neuromuscular junction. We have smallness in myopathy and large in re-innervation, but it does not say much about the axonal loss or conduction block. But if we take conventional EMG and look at interference pattern and quantitate that, then we differentiate not only myopathy and neuropathy, but we detect the axonal loss and abnormal central drive. If we have the macro EMG, I told you that is mainly to measure the electrical size of a motor unit, the total electrical size, and that is normal or small in myopathy and increased in re-innervation. motor unit number estimation is mainly concentrated on the number of motor neurons that are active. And transcortical magnetic stimulation, it is not used for myopathy re-innervation, but it is used to look at the central part of the motor unit. So, thank you very much.